mixed signal and low power verification in this track. We have 4 papers, and each of the papers are about 25 minutes long, including the Q&A session. The first paper is titled An Automated Approach to Mixed Signal Verification of Macros in a Cluster. The authors for the paper are Prabhat Bhatt, Amlan Chakrabarti, Girish AS, Aniket Bharat, and Shajo Mathew. They are associated with AMD India Pvt. Limited. On to the paper now.
Hello everyone, my name is Prabhat. Along with me, we have Amlan, Girish, Aniket, and Shajo, and we are presenting our paper today, which is an automated approach to mixed signal verification of macros in a cluster. So let me take you to the introduction. What's a mixed signal design? So a mixed signal design takes a real world analog information and converts it for the digital world to understand. And these mixed signal designs are way more complex in the digital only SoC. Why is there so much talk about mixed signal design in the past decades? This has come primarily from the fact that there have been new markets which have emerged in the past decade or so in AI, automotive, IoT, communication, hardware application industries. So they are fueling the demand for the mixed signal designs. And also they are revealing few shortcomings in our legacy mixed signal design methodologies and tools. And so SoC is catering to this increased need. And in that evolution, we are seeing several trends which we want to list out here. First is the increased use of analog IP. So since the SoC now requires a lot of interfacing protocols, so does the count of analog IP increases. This also is fueled by the use of power management units. A lot of current reference voltage designs are being used in the SoC, which increases the count of analog IP. So what it does, it creates a tighter interaction between the analog and digital blocks in the SoC. So the interaction between these two blocks within an SoC becomes more complex, and also they increase in numbers. So as more SoCs include more more mixed signal designs with more analog and digital blocks talking to each other, this complexity increases. And what it does is it creates a complexity in verification. So in order to have first-time silicon success, it's not only required to verify all the features of each macros in a cluster, but we need to verify all the use cases, all the real world scenarios, and that becomes very critical. So that puts a lot of pressure on the verification engineer to make sure that the design is robust and all the features are verified. So in this paper, we have taken I/O as an example. So let me brief you on I/O. So I/O usually sits at the periphery of the chip, and I/O cluster usually comprises the following: GPIO, which is a regular transmitter and receiver; a power OK block, which usually generates power on reset signals for a glitch-free operation; and an LDO, which generates a reference. It's a reference generator for the GPIO device and other IO devices. And then we have ESD, which protects the devices from high-level overstress and current surge ESD events. So this becomes a cluster, and at the IP level, we need to make sure that the cluster is itself verified as it's used in the real-world application. This reduces the SoC verification effort, because if we don't do it, any bugs gets identified at the SoC level, it's harder to track it and isolate it because the design is huge at the SoC level. But at the IP level, since the design is small, we can easily identify and solve the issue in the first place. So that becomes very critical. So that takes us to the problem statement that we have. In previous technologies, since clusters were not that important, So the mixed signal verification were limited to verifying individual macros. So we were verifying standalone, verifying each macros in a cluster in their own standalone verification environment, be it be small verification, it's a small macro or it's a large macro. We take it and verify it in their own environment. So for example, we have this GPIO environment, a sequencer in the agent, which generates sequences and drives data to the DOT, which gets converted from A to D and D to A. And then these inputs, which are support macro, which are used to come from support macros in the cluster, we generated from the test bench. So this is a generic model used with all the macros in a cluster. So what it does is, as macro scales and more macros are there in a cluster, this more we have more of these verification environment. So, and even for us, as I said, even for a smaller macros, we will build this environment. So it will take a lot of effort and takes a lot of time in verifying as the macro increases scales, and there are more chances of bug escape as we are driving these interface signals not from the test bench but the macro itself. So not from the macro but the test bench itself. So this may reveal a lot of bugs. But when the cluster became critical, it became imperative for the verification engineer to run cluster level simulation. So and in that objective, we faced a lot of issues that we want to list out here. First is the need for generating a single netlist view. This is very critical because we've seen that the simulator often takes only single netlist. If you have multiple spice netlists in a cluster, you'll find it difficult to give all those 5 as an input to the simulator. So that we need a way to create a stitched netlist view. That's what we call it, of multiple IPs. And the stitched netlist approach, they bring a lot of issues along with it. It brings port and naming conflict. So as you have multiple IPs in a cluster designed by independent designers, they don't know what each other are doing, right? What they are naming their port names, and what are the sub-circuit names, and what are the internal net names. So these naming conflict arise when you cluster them together. So that needs to be addressed. Along with that, A to D and D to A conversions becomes very critical in the cluster level simulation, since these macros are talking to each other. So, and all these interfaces are coming, interface signals are coming from the macro itself now. So that makes A to D and D to A conversion even more critical. So we are just exploring one of the example here. Suppose we have a supply ramping up, and along with it, we have IOSM out, which is IO support macro output, ramping up slowly. It's an analog output. For example, if you gave a wrong conversion rule from analog to digital, and somehow you realize this logic 1 a little earlier than it's supposed to. So it's supposed to be logic 1 here. Now, because you have given it wrong, it's here. So it creates a noise on the pad, since noise depends on this output. And this noise goes down the logic and creates more issues, and creates a lot of debug, involves a lot of debug to identify and isolate this. So this we need to be very careful about. So as you would see, the correct behavior is this: when it should have been realized to logic 1, the pad would have been clean and no issues downstream. We also need to be wary of the simulator optimizing these interface signal as through net. That is one of the issues that usually happens in the cluster level simulation, and we need to deal with that too. Also, the challenge was in automating this mixed signal environment. So we have lack of assertion and coverage in mixed signal simulations. And why do we not have assertions in mixed signal simulations? It's because mostly served for the digital world, used in more mixed function sims, and we really we don't have a way to have to include these assertions, which is distinct component in an analog simulator view. So if you open even if you run or enable these assertions in a mixed signal environment and view them in a will form, or try to view them or debug them, these in the nodes in the assertions, you won't be able to see them, or you won't be able to identify them. They won't have a valid data, and so you won't know whether the assertions are running or even doing their job. So that's why we disable the assertion. Also, there's a in analog simulator, often we've seen that the digital view is very limited. So the analog simulation, the analog waveform is way ahead in time, and digital simulation lags behind. It's because there is a big inconsistency in the simulators. So um, so that also, this is a DV engineer to enable these assertions, and so we disable the coverage too for the same reason. And other than the reason that I mentioned for the assertion, the other reason is why we disable for reason for disabling the coverage in mixed simulation is that we don't know what to cover actually. Since these are real analog simulation, analog nodes are real values, they're not quantifiable, and they're not digital like 0 and 1, right? You cannot quantify them. So for example, if we take toggle coverage, so we won't know what to cover in toggle. So so that's the reason why we keep these switches off when we run mixed signal simulations. And what it does is it puts a lot of effort on the verification engineer to visually verify these uncovered scenarios, make sure the test bench has does hit all the scenarios. Like you see on the right, all the scenarios, the green are covered, but if any one of the sequences miss, so you don't know whether that may cause a potential bug, and that would have revealed a potential bug had it been hit. So that is very that becomes very critical, and lack of it puts a lot of effort on puts a lot of load on verification engineer to verify them through waveform debug. And that approach is of course cumbersome, takes a lot of time, and creates can be bug prone. And ideally verification should depend less on vision, more on automation, and that will make the verification more robust. So this is the proposed solution for cluster level simulation. We have the environment with multiple agents and parallel sequences being driven through them, and all the DUTs, the interface signals are coming from the macro itself, and they are connected through A to D and D to A conversions. And this is an advanced UVM model from the simplistic one. And then for the cluster simulation, we use the internal script to stitch the netlist to feed it to the simulator, and then we specify to the simulator that we need to simulate all the top levels that we are giving it to them. Then we need to specify the config command to fix the duplicate nodes and sub-circuit issues, and also specify E2D and D2A conversion rules. And also we use the same config commands, the config file, to avoid the TrueNet optimization. So they are ways to do that too. So step towards automation. So we have a very interesting way to make sure we implement assertions and coverage in mixed signal simulation. So for that, the first step is to create a DUT monitor and connect it to the DUT, so that all the ports in the DUT monitor are input, and it's bounded to the DUT. And this is the DUT. This DUT monitor is used to write assertions and do coverage on. And what to do after that is create an empty SPICE instance of this monitor and plug it to the SPICE top. So what the cluster netlist view will have, we just plug this this SPICE this empty shell into the SPICE the cluster view, and then we specify to the simulator that do not use this SPICE empty SPICE instance that is added to the netlist, but instead use the Verilog. So which can be done. It's doable in most of the simulator. And then you use the simulator, the DOT monitor, to run assertions and do coverage on. Along with that, we need a way to bypass the fact that the simulator often lacked consistency in dumping digital waveform. So we develop a model, a forever loop in TB-top, which after 1 microsecond of delay dumps using FFTB VAS and FFTB dump file. It dumps digital waveform. So this way we get a consistent, continuous digital dump if the simulator when the simulator doesn't do that. So this is a complete solution. We have a DUT monitor, and which is connected to the DUT, and then we have this spice top clustered view with a monitor in it, empty shell, and we have told the simulator to use Verilog instead of this. And this makes the simulator compile this DUT monitor along with the analog simulation, and then this digital monitor can now be used to run assertions and do coverage analysis on. And that's a consolidated view of our whole. This is a fully automated mixing environment view that we wanted to share. So we come to the results and observation. So after running the mixed signal verification in the cluster, we see significant time improvement in verification. So this comes from the fact that most of the small macros in a cluster usually get verified within a cluster level single simulation itself, any power up, power down, for example. So that reduces a lot of verification effort and saves a lot of time. And also we were able to identify issues in clusters within the IP and not let it percolate to the SoC. So that was significant. And at the since the SoC it takes a lot of time, so we significantly improved on the robustness of the design as well. Now we come to the results for the automation. So the way in which we proposed the solution, we implemented that in one of our mixed signal simulation. We wrote the assertions in the DUT monitor. We detected few assertion failures, and we were also able to debug them through waveforms. And we had assertion counters which guaranteed whether the assertions actually clicking or actually doing its purpose. And at the same time, we had assert coverage enabled, and that was also guaranteeing the assertions are running or not. Also, we have coverage enabled at this time on the DUT monitor, and we see this results, which is quite interesting. We see that this is in general view that you usually see in function sims. So you see these port toggling either 1 from 0 to 1 or not. You can actually see R12 is not moving from 1 to 0. But that is because it's always on supply. So you can see what's the toggle number, what's the assert coverage number, what's the line coverage, and you can without looking at the waveform, you can know a lot about the test bench from this whole view. So assertion, as you know, validates the correctness of the design, and coverage validates the test bench itself. So if enabled, this herald a shift left approach in mixed signal verification. This enables us to address verification holes quicker and more efficiently and effectively. We'll come to the key takeaways quickly. Just a highlight. So automation, as you know, improves the quality of verification, which we are trying to address and bring to the mixed signal environment. And cluster level design verification methodology verifies the real world scenario. Feasibility part, we have already incorporated the cluster verification in various AMD SoCs. We have proposed methodologies are very general. They can be implemented wherever a cluster can be formed. On efficiency, accuracy, yes, automation eliminates human efforts and errors, and bugs within a cluster due to cluster level simulation can now be found at the IP level rather than the SoC. That saves a lot of time. Effectiveness, yes, faster turnaround time, as we said, and exhaustive and robust verification of cluster from macro. So that brings to the end of the PPT. Please let me know if you have any questions. Thank you for listening. Have a good day.
Hello.
Hi, Loga sir. My name is Amlan Chakrabarti. Can I start? Can I take the question which I see on the
Yes.
panel?
So let me
Sure.
thank you very much for this paper. I think this was an excellent paper that tackled a new area basically in mixed signal design. And before we just, I had a couple of questions. One is, what is the when you talk about coverage and also the assertions, right? How does the what did you have to modify from the existing system Verilog assertions and coverage to make this methodology work?
Okay, so it was not. So the main problem was that how do we implement assertions? How do we implement assertions in a way which can be accepted in the mixed signal environment? So that's why what we have proposed in the paper is, what we have done is that we implemented a digital monitor, and then we plugged empty module in the SPICE netlist, so that because SPICE needs to have a placeholder, right? So we introduced an empty placeholder in the SPICE netlist, and then made sure that when we run, so regardless of whichever tool we use, we always need to give a uSPICE sort of something similar syntax to pick up a SPICE netlist. In this case, we made sure that we instruct the simulator to use this Verilog module. So that's what we did to pick up this digital monitor. Once that was in place, we were able to implement assertions in the digital monitor pretty much the same way as we do in functional simulation. So that helped us. So when the mixed signal simulation runs after that, the assertions were getting run, which helped in the debug, as well as we were able to implement the subsequent coverage, because we have now the assertions in place. And one more point, which probably we didn't highlight that much, is that it helped a lot. We are now in a position to run regressions, because we no longer rely on visual checking. We have assertions, so we can debug waveforms. We can debug regression phases.
Yeah, there's a question from the audience, I think. Yeah, the question is about the debug impact of doing this cluster level mixed signal simulation. So would you like to comment on that?
Yes, sure. So very good question. So we didn't plan to say that the cluster level simulations totally obviate the need for a macro level simulation. This of course depends on the cluster. So our cluster consisted of a general purpose IO, macro which generates power is okay or power good, LDO, electrostatic discharge macro, pretty complex cluster. But at the same time, the benefit which we saw was between cluster level and SOC level simulations. So in the sense we verified at the cluster level, we were able to prefetch many of the issues which a SOC level simulation would have caught, but far later down the cycle, which would have caused impact to the execution, debug, and everything. Coming to the specific question, I agree. There will still be cases where even though we do a comprehensive debug in cluster level simulation, we may have to go deep down into individual macros and debug issues from there. So I will not go to the extent of saying that with this approach, we totally eliminate the need for any macro level debug. But the comparison we have tried to show is between cluster level and a higher level, a SOC level verification. There may still be cases where macro level debug will be needed to debug issues which are deep rooted in the macro.
Thank you very much, Amlan, for your presentation, and Prabhat for your presentation and the paper and the question answers. So in the interest of time, I think if there are more questions, we can talk to the authors directly. We'll move on to the second paper in this track. Thank you so much.
Thank you, Loga sir. Thank you, everyone.
Thank you so much.